In order for us to really talk about fluids in a realistic sense, it involves solving some very difficult and complicated coupled differential equations um, that are highly nonlinear and that are very difficult to solve. In fact, a lot of them can only be solved numerically and simulated. So, for this reason, we're not going to go in much into any kind of into detail in dynamical fluids. We'll have some very simple cases that we're going to discuss in Unit 19. But here in Unit 18, we're going to be talking about static fluids. And we're going to be talking about fluids that are incompressible and ideal. Okay? So by ideal and incompressible, we're saying that there's no viscosity. In other words, imagine we have a pipe. Okay? If we have a real fluid in it like water, okay? For one, you can have, viscosity. So if you think about something other than water, if you think about something like molasses, right? You know that it flows very, very slowly because of the interactions of the fluid with itself. Okay, we're going to be ignoring those types of things. So there's going to be no viscosity. But viscosity is basically kind of a type of friction. But we're also going to be ignoring another type of friction, and that's the friction that we have up against the pipe, right? Because as you can imagine, this pipe, if we were to, kind of zoom in on an area, would, even though to us it looks very smooth, we would see all these dents and grooves, and then, our little water molecules are just going in there, and, they're bumping around on these things, and so that's causing friction, so that's causing it to move slightly slower on the edges than it is in the middle. Okay. So again, so basically, this is kind of the equivalent of what we did before when we ignore friction, right? When we first started looking at a lot of our forces, we just ignored friction. We said it's easier to just to put it in later. Whereas in the case of fluids, we're not even going to put it in later, with the exception of one equation that we're going to look at the very end of Unit 19. Okay, by saying that they're incompressible, what we mean is, let's say we have a container of water, okay, and on top of that water I put a platform, and I make it so it's perfectly flush against the sides. So in other words, like if I, there's no way that any water can slip up, from the sides, okay? We're saying that that's not going to happen. It perfectly fits the container, okay? And then let's say I put a car on top of this platform, right? Well, realistically, we know that a car is very heavy, right? And so, so it doesn't go down as much as you would think it would. It actually would only, the platform would only, realistically, only go down a very small amount, because something like a tank of water actually is very incompressible, but not completely. But we're assuming that it's completely incompressible, meaning it's not going to be, that if we performed this experiment, the car wouldn't move down at all. And to a very good approximation for a lot of fluids and a lot of situations, we can do this. And so because of that, so I just want to get it out the way that these are the two, kind of big approximations that we're making throughout this entire unit and throughout Unit 19. And I also want to stress that this isn't really, kind of fluid mechanics. This is much more of an engineering application than this is actually physics, the things that we're doing now. It's, in both of these units, I'm going to throw a few equations at you. I'll slightly derive some of them. And then you're basically just going to plug and chug problems. So for those of you that, have pretty good math skills and are, kind of sick and tired of a lot of the conceptual physics, then you'll probably like this as a nice break. But if you like actually, kind of learning new things and understanding how things are working, this unit isn't as interesting when it comes to that.